Hi, my name is Megan Sandoval, and I'm going to be giving you a brief talk on mass spectrometry and spectroscopy. So to start off with, I have a definition right here of what mass spectrometry is. It's basically an analytical technique that measures the mass-to-charge ratio of charged particles. And it works by ionizing chemical compounds to generate charged molecules and measuring their mass-to-charge ratio. So I want to give you a brief kind of principle that relates to this. So suppose you were standing right here and you shot a cannonball out and it was coming straight towards you. So here's your cannonball. And you want to deflect this cannonball out of your path and around you so you don't get hit by it. But all you had was a hose and a jet of water. Now, since that cannonball is so heavy, it's probably not going to be deflected out of your path because the jet of water isn't strong enough. So what's going to happen? It's going to continue on a straight path, not be deflected, and probably end up hitting you. Suppose instead you shot a tennis ball towards you. And this ball was moving at the same speed with the same force. And as I said before, all you had was the same jet of water to move it out of its path and be deflected around you. Now, the tennis ball is much, much lighter than a cannonball. So most likely this strong jet of water would be able to move it out of your path and not hit you. So the amount of deflection you get for a given sideways force depends on the mass of the ball. If you know the speed of the ball and the size of the force, you could then detect the mass of the ball if you knew the amount of deflection that it took along some pathway. The less deflection, the heavier the ball, and vice versa. So you can apply this exact same principle to atomic-sized particles, and that's basically what happens in mass spectrometry. So how this all works is through four main stages, and these include ionization, acceleration, deflection, and detection. In ionization, an atom is ionized by knocking one or more electrons off to give a positive ion, and this always works with positive ions. In the next stage, acceleration, ions are accelerated so that they all have the same kinetic energy. In deflection, the ions are deflected by a magnetic field according to their masses. And this relates to the example I said earlier. You have a lighter particle, you have more deflection. A heavier particle probably have less deflection. And another example is the more an ion is charged, the more deflection you get. So, say for instance you have a mass 28 and a charge of +1. Your mass to charge ratio, which is expressed as m/z, would equal 28. So then the next stage is detection. And this is when a beam of ions passing through the machine is detected electrically. And if you vary the magnetic field, you can bring each ion stream in turn onto the detector to produce a current which is proportional to the number of ions arriving. So basically to show how this all works, I have a diagram right over here. Now this isn't exactly what a mass spectrometer looks like, but it can show you the main parts that go along. So here you have the probe, and you have your sample which you put right here, and then it moves through the flight tube onto the detector. So as I said before, here's where your ion source is. So here's where the stage of ionization occurs, and then here's the stage of acceleration. So then your particles move through, and this big unit right here is the magnet. So that's where the deflection occurs. So as you see right here, I have arrows going up and down. And the arrow going up shows ions that are too heavy end up bending too little, and ions that are too light bend too much. So only the ions that are the right mass can enter the detector down here. And this right here is the detector, which in turn is where the stage of detection occurs. And it moves on through to the recorder, and then you end up getting a mass spectrum. And there's three main modules in this mass spectrometer. The first is the ion source, as I showed earlier, which converts gas molecules into ions. The second is the mass analyzer, and this sorts ions by their masses by applying electromagnetic fields. And the third is the detector, which measures the value of an indicator quality. And this provides the data that you end up getting in your mass spectrum, which you can calculate the abundances of each ion. So here I have an example of a mass spectrum, and this is for molybdenum. And you can see on your vertical axis here you have your relative abundance. And this is related to the current received by the chart recorder. The greater the current, the more abundant the ion. And on your horizontal axis you have your mass to charge ratio, which ends up being your molecular weight. So here for molybdenum, you can see you have different peaks around 92, 94, 95, 96, 97, 98, and 100. You see the tallest peak is at 98. And the way to interpret this is your most common ion for molybdenum. So it has a mass to charge ratio of 98. And then you can see your least common ions would be around 94 and 97. And basically, if you assume that these ions and isotopes have a charge of +1, then this means that the masses of these isotopes on a carbon-12 scale would be 92, 94, 95, 96, 97, 98, and 100. So basically there's 7 different peaks here, so 7 different isotopes for molybdenum. So related to basically what I just said, the main applications of mass spectroscopy are both qualitative and quantitative. Qualitatively, you can identify unknown compounds. You can also determine isotopic composition of elements in a molecule, and you can determine the structure of a compound by observing the fragmentation. Quantitatively, you can quantify the amount of a compound in a sample, and then you can calculate relative masses, just like I showed here. That's mass spectroscopy in a brief overview, and I hope you learned something.